There's a story people reach for when the world begins to feel thin. They say it is a simulation. They mean that somewhere behind all of this, there's a real machine running a real program, and that what fills the eyes and the hands is only the picture that program draws. It is a frightening story on its surface, but underneath it is surprisingly consoling, because the simulation story, for all its apparent radicalism, never once questions whether there is a floor. It only moves the floor further away. Somewhere in the story, there's still a real room, a real computer, a real base level where things are finally, solidly what they are. And here is where physics enters, quietly, and removes the floor. Not the floor of this particular story, the floor of every story like it, the floor of the entire idea that reality, at some level deep enough, is made of definite things sitting in definite places, waiting to be found. For most of human history, this was not an assumption. It was not even a position. It was the shape of what the word real meant. The moon is there when no one looks. The coin in the closed box is already heads or already tails. The electron, wherever it is somewhere. These were not philosophical claims. They were the unspoken grammar of every serious investigation into the world, the grammar of science, of common sense, of every attempt to understand anything at all. In the first decades of the 20th century, that grammar broke. It did not bend under pressure. It did not develop exceptions at the margins. It broke at the center, in the most controlled and careful experiments ever designed, with results that have since been confirmed in dozens of laboratories across 6 decades, with loopholes systematically closed one by one until none remain. The verdict is not subtle, and it is not contested among the people who actually understand the experiments. The verdict is that the world, at its smallest and most fundamental scales, does not have definite properties before those properties are measured. Not that we cannot know what they are, that they are not there to know. This is the thing that needs to be said clearly before anything else, because the popular version of this story is not the real story. It is often said that the observer creates reality, that consciousness, by looking, reaches into the quantum world and makes it solid. This is repeated so frequently and with such apparent authority that most people who encounter quantum physics for the first time assume it is what the physics says. It is not. The error is old and it is understandable, but it is wrong in a way that matters. When an experiment detects which path an electron took, the detecting does not require a mind. A photographic plate will do it. A Geiger counter will do it. A scratch on a cold metal surface left unread in a dark room will do it. Whatever the act of measurement is, it is not the touch of awareness that changes the result. The physics does not say you are the author of the world. The physics says something stranger than that. Something that does not flatter the self at all. Something that, when followed to its conclusion, makes the very concept of the self considerably harder to locate. The break came from the smallest things. A single electron, sent toward a barrier with 2 narrow openings, does not behave the way a thrown stone would. It does not choose one opening or the other. It arrives on the far side as though it had somehow passed through both and interfered with itself, and arranged the possible landing places into a pattern. Bright bands and dark bands, stripes of possible and impossible, that no object traveling a single path could ever produce. And when those electrons are sent one at a time, alone, with long silences between, nothing in the apparatus but a single electron moving toward a barrier in the dark, the pattern still builds. Slowly, over many electrons, each one arriving and registering as a single point. Dot by dot, the interference stripes reappear. Each electron knows the other slit was there, even though nothing was there to know it. There is something vertiginous about sitting with this for a moment. Not as a thought experiment, as a fact. The pattern is not produced by many electrons interacting with each other. It is produced by each electron interacting with its own possibilities, with the paths it could have taken, with the question that was never asked. The mathematics that describes this does not say where the electron is. It says, for every place the electron could be, how strongly the world leans toward finding it there. Before measurement, the electron is not in one place with an unknown location. It is a spread across all possible locations, weighted by tendency. It is a leaning, a probability not yet made into a fact. And then comes the look. Place a detector at one of the openings to see which way the electron went. The moment the detector registers a distinction, the spread collapses to a point. The leaning becomes a fact. The electron is suddenly here and not anywhere else, and the pattern of all paths at once vanishes from the far wall as though it had never been. Not fades, vanishes. This is the measurement problem. It has been open for 100 years. It is the central unsolved question in the foundations of physics. The Schrödinger equation, which governs how quantum systems evolve in time, is perfectly deterministic. It says nothing at all, about when or why the spread should collapse to a single outcome. The collapse happens. The experiments confirm that it happens. And the equation that governs everything else in quantum mechanics has no mechanism in it, no term, no clause, no footnote that says when or how or why. No one has closed this. The old answer was that the electron has a real location all along, that the spread is just ignorance, our ignorance, not the electron's nature, that underneath the wave function there are hidden facts we cannot yet access, and if we could, we would find the world as solid and definite as the grammar of common sense assumed. This answer is comfortable. It is the simulation story wearing different clothes. It keeps the floor. It only hides it. In 1964, a physicist named John Bell, working quietly at CERN in Geneva, proved that this answer cannot be saved. Bell showed, in a mathematical proof that has never been refuted, that if the particles carry their properties with them, hidden but real, then those properties must obey a certain limit on the correlations they can produce between distant measurements. He derived an inequality, a numerical bound, an upper limit on how strongly the results of separate experiments can be correlated, if the results were always determined in advance. The experiments since have measured that limit. The world breaks it. Not slightly. Not within the margin of uncertainty. The violation is substantial, consistent, and reproducible. The hidden properties are not hiding. They are not there to hide. The floor is gone, not pushed deeper, not obscured, gone from the architecture of reality at the level where the architecture can be examined. So, the question becomes what stands in its place. And this is where the simulation story collapses entirely, and something stranger stands up behind it. The simulation story needs a base level of definite things. A computer must run on something. Bits must sit somewhere. If there is no base level of definite local properties, if properties themselves are events rather than foundations, then there is nowhere to put the machine. There is no room the machine sits in. A world made of answers to questions it poses to itself has no substrate in which a simulator could be installed. What some of the most serious physicists of the last half-century have proposed, not as metaphor, not as poetry, but as a technical conjecture about the structure of reality, is that the deepest layer is not matter, and not a machine, but something closer to information, not information stored in a medium, information as the medium, the bit, the yes or the no, the distinction drawn, the answer registered, as the fundamental unit from which everything else, including space and matter and time, may be derived. This is stranger than any simulation, much stranger. A simulation has an outside. There is a programmer. There is a wall the machine stands against. The proposal that has emerged from quantum foundations has no outside. There is no view from nowhere. There is no perspective from which the whole thing is visible as a thing. There is only the world, registering distinctions about itself, answering questions it poses to itself, with no floor beneath the answering and no ceiling above it. What is a world with no floor? What is real in a reality where definiteness is an event and not a foundation? What is left when the last solid thing dissolves and does not leave emptiness behind it, but something else? Something the language of objects has no good word for. These are not small questions. They are not the questions of a particular discipline, and they are not new. Long before anyone built the detector, long before the vocabulary of wave functions and measurement and collapse existed, there were people who pursued the same dissolution by entirely different means. They sat in silence. They looked closely at experience. They followed the question of where definite things come from, and whether the solid core of anything, a thought, a sensation, the sense of being a self, can actually be found when searched for carefully enough. And they came back with reports that the physicists would not arrive at for 2,000 more years. They reported that the search comes back empty, that the definite thing expected at the center is not there, that what is found instead is not nothing, but something that the language of objects cannot hold, something that does not collapse into a point under the look, something that may in fact be what the look is made of. There is no name for what these people found that does not immediately mislead. The night will return to them, slowly, without hurry, from several directions at once. Not to claim that they knew first, not to suggest that one field validates the other, or that contemplative practice predicted experimental physics, or that the equations of quantum mechanics are somehow encrypted in ancient texts. That framing is comfortable, and it is false, and it does a disservice to both fields. The languages are different. The methods are different. What the people in the laboratories found and what the people in the silence found are not the same thing. But the shape of what they found, the shape of the question they were left with, is worth looking at carefully, which is a different claim and a more honest one. For now, it is enough to let the floor go, to sit with the absence of a base level, the way you might sit in a dark room and feel, for a moment, the room not be empty. That feeling, the sense that the nothing is not quite nothing, has a name in physics now. The night will find it. The electron is still leaning across its paths, before the look, neither here nor there, neither real nor absent, suspended in the open field of what the question has not yet forced it to be. The architecture is beginning to rise. The question did not begin with electrons. It began with a confidence so complete that it did not feel like a position. It felt like the world. In 1814, the French mathematician Pierre-Simon Laplace wrote a thought experiment that became the clearest statement ever made of what physics, at its foundations, had assumed. He imagined an intelligence, not a god, but a calculation. that knew the precise position and momentum of every particle in the universe at a single moment in time. Such an intelligence, Laplace wrote, could calculate the entire future and the entire past from that one instant. Everything that would happen was already determined. Everything that had happened was already fixed. The universe was a mechanism, vast and intricate, running on laws as dependable as arithmetic. And every particle in it, at every moment, was exactly where it was, doing exactly what it was doing, whether or not anyone was looking. This is the world physics inherited, not as a theory, as the shape of what the world meant. It was a beautiful shape. It had explanatory power far beyond anything that had preceded it. Newton's laws, Laplace's intellect, Maxwell's equations. Together they described the motions of planets and the propagation of light with a precision that felt, by the end of the 19th century, almost supernatural in its accuracy. There were a few loose threads, small anomalies, puzzles at the margins, but most physicists of 1890 believed they were close to the end. A few more decades of refinement, and the description would be complete. The loose threads pulled the whole fabric apart. In 1900, a German physicist named Max Planck was trying to solve a narrow technical problem. How does a heated body radiate light? And at what frequencies? The classical answer predicted catastrophe. It said a heated object should radiate infinite amounts of energy at high frequencies. A result so obviously wrong that it was called, with dry humor, the ultraviolet catastrophe. Planck found a mathematical fix. He assumed, as a mathematical trick he did not fully believe, that the light was not emitted in smooth, continuous streams, but in discrete packets. Quanta. Chunks of energy, each one proportional to the frequency of the light. His formula worked. It matched the experiments with startling precision. He spent years trying to find a way to derive the same result without the packets. He never found one. The packets were not a mathematical trick. They were the world. Einstein went further. In 1905, working in the Bern Patent Office in Switzerland, he proposed that light itself, not just its emission, but its nature, was made of discrete particles, photons. He used this to explain the photoelectric effect, which classical wave theory could not explain at all. Why metal, struck by light below a certain frequency, emits no electrons, no matter how intense the light, while light above that frequency always ejects electrons, even at very low intensity. The explanation required the particle picture. And it worked. Neither man was comfortable with what they had found. The world was not continuous. Something in its grain was irreducibly discrete. The smooth floor had developed a structure, but the real break was still ahead. The wave function arrived in the mid-1920s, and with it a mathematics so powerful and so strange that physics has not fully digested it since. In 1925 and 1926, Werner Heisenberg in Göttingen and Erwin Schrödinger in Zurich developed, by entirely different routes, equivalent mathematical frameworks for describing the behavior of quantum systems. They were not trying to describe different things. They were trying to describe the same thing, and they arrived at the same structure from opposite directions. Heisenberg used matrices, arrays of numbers representing the possible transitions between states. Schrödinger used waves, functions that spread and interfere and evolve continuously through space. Paul Dirac in Cambridge later showed they were mathematically equivalent. Two languages, one structure. Schrödinger's version, the one that became the standard pedagogical tool, described a quantum system through a wave function, a mathematical object that assigns to every possible configuration of the system a complex number, a kind of amplitude, not a probability directly, an amplitude, a number that can be positive, negative, or complex, and that carries information about both magnitude and phase. The amplitude squared gives a probability. The probability of finding the system in that configuration if it is measured. This is the Born rule. Max Born in Göttingen proposed it in 1926, in a paper he later said he had been uncertain about. It is now one of the most precisely confirmed rules in all of science. The predictions it generates for the spectra of hydrogen, for the behavior of semiconductors, for the outcomes of every particle physics experiment ever run, are correct to a precision that has no rival in any other physical theory. But it is worth pausing to notice exactly what it says, and more importantly, what it does not say. It says, if you measure the system, you will find this result with this probability. It does not say where the system is between measurements. It does not say the system has a definite configuration between measurements. It is silent on what the system actually is when no one is asking. The silence is not an oversight. It is not a gap waiting to be filled by a better theory. It is a deliberate agnosticism built into the structure of the formalism. And it is exactly this agnosticism that has made quantum mechanics philosophically unfinished for 100 years, while being scientifically triumphant for the same 100 years. The theory works with a precision unmatched anywhere in science, and it leaves completely unanswered the question anyone who thinks about it for 5 minutes will ask. So what is the electron between the measurements? The double-slit experiment makes this question visible in its sharpest form. A single electron, heading toward a barrier with 2 narrow openings, produces, over many such electrons, sent one at a time, an interference pattern on the screen beyond. Bright bands where many electrons arrive, dark bands where almost none do. The pattern is the signature of a wave passing through both openings simultaneously, the 2 wavefronts overlapping and reinforcing each other in some places, canceling each other in others. And yet each electron arrives as a single point, not spread across the screen, a dot, here and nowhere else. The interference pattern is built dot by dot, one at a time, in the dark. The wave function tells you where each dot is likely to land. It does not tell you where this particular dot will land. The Born rule converts the amplitude squared at each position into a probability, and the probability is confirmed statistically as the pattern builds. Place a detector at one of the openings to find out which slit the electron actually used, and the interference pattern vanishes. Not fades, vanishes. The electron now lands in one of 2 clusters, corresponding to one slit or the other, with no interference between them. The act of asking which path was taken changes what arrived on the far side. The wave function before the detector is a superposition of 2 paths. The electron threading slit 1 and the electron threading slit 2, both present as amplitudes, not as alternatives. When the detector registers, the superposition collapses to 1. A definite outcome emerges from an indefinite state. The Schrödinger equation has no term that describes this collapse. The Born rule tells you what probabilities to assign to the outcomes. Neither the equation nor the rule explains why a definite outcome occurs at all. The silence is not an oversight. It is the gap the measurement problem falls through. The Schrödinger equation, which governs how the wave function evolves in time, is continuous, deterministic, and linear. It does not collapse. It spreads. It allows all possible configurations of a system to coexist, weighted by their amplitudes, evolving according to the equation's smooth flow. But experiments produce single, definite outcomes. An electron hits the detector at a single point. A measurement returns a single value. Nothing in the Schrödinger equation predicts this. There's no term in the equation that says, here, now, the spread collapses. There's only the spreading. And then, when a measurement is made, a definite result. In 1935, Schrödinger tried to show how strange this was by constructing a thought experiment. A cat is placed in a sealed chamber with a radioactive atom and a mechanism that will release a lethal dose of gas if the atom decays. Quantum mechanics says the atom, before measurement, is in a superposition of decayed and not decayed. But the mechanism connecting atom to cat is classical. If the atom is both, is the cat both? The cat, before the box is opened, is, according to the equations, simultaneously alive and dead, not in an unknown state. Both. This is what the mathematics implies if no special collapse rule is introduced. Schrödinger did not think this was the correct picture of reality. He thought it was a reductio ad absurdum. He was right that something had gone wrong. He was wrong that it was the mathematics. The mathematics was fine. What was wrong was the assumption that the everyday world and the quantum world must follow the same rules. The measurement problem is not about cats. It is about the gap between the smooth, deterministic, spreading evolution of the wave function and the single, definite, apparently random result that measurement always produces. The gap has not been closed. It has been papered over with interpretations, and the papering is where most popular accounts of quantum mechanics quietly stop being accurate. There are several major interpretations, and they are not minor variations on a theme. They are genuinely different proposals about the nature of reality, and they cannot all be right. The Copenhagen interpretation, associated primarily with Bohr and Heisenberg, says the wave function is not a description of a physical system, but a calculation tool for predicting measurement outcomes. Collapse is not a physical event, but the updating of a calculation. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, every measurement outcome occurs in a continuously branching tree of parallel realities, and collapse is only the appearance of one branch from within another. The pilot wave interpretation of Louis de Broglie and David Bohm says particles have definite positions all along, guided by a real wave, and the randomness of measurement reflects our ignorance of the initial conditions. Objective collapse theories, like the GRW model proposed by Girardi, Rimini, and Weber in 1986, say collapse is a real physical process governed by a new law of nature not present in standard quantum mechanics. Relational quantum mechanics and cubism take yet other positions. These interpretations make the same predictions for every experiment that has been performed. They are empirically equivalent in all known cases. This is the honest position. After a century of the most successful physical theory ever constructed, physicists do not agree on what the theory means. The predictive success and the interpretive chaos coexist with no apparent tension because the predictions work whether or not the interpretation is settled. No one has closed the measurement problem. This is not a provisional state pending a few more experiments. It is a deep disagreement about the structure of reality that the experiments themselves, so far, cannot adjudicate. So consider what the question looked like to the people who were actually there. In October 1927, the greatest physicists of the century gathered in Brussels for the 5th Solvay Conference. Niels Bohr, the Danish architect of the Copenhagen interpretation, was there. Albert Einstein, who had started the whole affair and then recoiled from where it led, was there. Heisenberg, Born, Pauli, Dirac, Schrödinger, de Broglie, a room full of people who between them had built the entire structure of quantum mechanics and who disagreed profoundly about what they had built. Einstein did not dispute the mathematics. He disputed its completeness. His objection was not, as it is sometimes caricatured, sentimental. He believed that a description of nature could not be complete if it was fundamentally probabilistic at its core. Not because God should not play dice, but because probability, properly understood, is always a statement of ignorance about something we could in principle know. The electron, in Einstein's view, had a definite position and momentum, even when we could not measure both. The wave function was a useful summary of our ignorance, not a complete account of the electron's nature. The hidden floor was still there. We just could not see it. Bohr's answer was more radical and more difficult to hear. Bohr held that there is no quantum world. There is only an abstract quantum description. It is meaningless to ask what the electron is doing when it is not being measured, because the question presupposes a reality independent of the act of measurement, and quantum mechanics gives no warrant for that presupposition. The wave function is not a picture of the electron. It is a tool for calculating the results of experiments. The floor is not hidden. The floor is not the right concept to apply. They argued for decades. Einstein never accepted Bohr's position. He died in 1955, still searching for a deeper theory, still convinced that the wave function was incomplete. In 1935, Einstein, working with Boris Podolsky and Nathan Rosen in Princeton, published what he considered his most decisive challenge to quantum completeness. The EPR paper, named for its three authors, described a situation in which two particles interact and then separate. Once separated, a measurement of one particle's momentum instantaneously fixes what will be found when the other particle's momentum is measured, regardless of how far apart they are. If the measurement is of position instead, the same instantaneous correlation holds. Einstein argued this proved one of two things. Either the quantum description was incomplete, the particles had these correlated properties all along, or measuring one particle instantaneously influenced the other across any distance. The second option, action at a distance, violated special relativity. Einstein found it unacceptable. So the first option must be true. The wave function was incomplete. Hidden properties existed. Bohr responded within months. His response was dense and, by his own admission, not easy to follow. But its core was this. The question of what properties the unmeasured particle has before the measurement is made does not have a well-defined answer, because the meaning of any property is defined by the experimental arrangement that measures it. The two experimental arrangements, measuring momentum versus measuring position, are mutually exclusive. You cannot do both, and the properties they reveal cannot both be simultaneously real in any operationally meaningful sense. It was not a satisfying answer. Even Bohr's supporters found it hard to articulate, and Einstein was not persuaded. He thought Bohr was avoiding the question rather than answering it. He was not entirely wrong. The argument mattered because it was not philosophical decoration. It had empirical content. If Einstein was right, if there were hidden properties, real and local, determining the outcomes of quantum measurements before the measurements were made, then there would be a way, in principle, to tell. The question was whether anyone could find it. In 1964, a physicist named John Bell, working at CERN in Geneva, found the way. Bell's insight was precise. If particles carry hidden properties, real values of spin or polarization determined before measurement. And if those properties cannot be influenced instantaneously by events at a distance, then there is a mathematical constraint on how strongly the results of measurements on separated particles can be correlated. He derived an inequality, a specific numerical upper limit. If local hidden variables are true, the correlations between distant measurements must stay within this limit. No exceptions, no loopholes in the logic itself. The argument runs like this. Imagine two particles, entangled and then separated. Each particle reaches its own detector. Each detector can be oriented along any of several directions. If a particle carries a definite hidden spin before measurement, the correlation between the two detectors' results will depend only on the angle between their orientations, predictably, classically. And for any combination of three measurement directions, the correlations must satisfy a specific algebraic inequality. Bell derived the original version. John Clauser, Michael Horn, Abner Shimoni, and Richard Holt later refined it into a more convenient experimental form, the CHSH inequality, which states that a particular combination of four correlation values must be less than or equal to 2 for any local hidden variable theory whatsoever. Quantum mechanics predicts a maximum value of 2 times the square root of 2, approximately 2.83. The violation is not marginal. It is not a matter of experimental precision. The two pictures make different numerical predictions, and those predictions are distinguishable by experiment. This was the moment the floor became testable. In 1972, in a basement laboratory at the University of California at Berkeley, two physicists named John Clauser and Stuart Friedman conducted the first experimental test of Bell's inequality. They used pairs of photons with correlated polarizations, separated them, measured each one's polarization along different directions, and compared the results. The correlations violated Bell's inequality. Local hidden variables were wrong, but the experiment had loopholes, technical imperfections in the detectors, questions about whether the measured sample was representative, that allowed a committed skeptic to maintain the old position. The loopholes were taken seriously, not as excuses, but as genuine questions about whether the test had been decisive. And so the experiments continued. In 1982, at the Institut d'Optique in Orsay, France, a physicist named Alain Aspect conducted a more refined version of the experiment, closing one of the main loopholes by switching the measurement settings while the photons were in flight. The violation remained. The settings could not have been communicated between the photons in time. Still, other loopholes remained open: detection efficiency, the coincidence time window, and the argument continued. By 2015, two major experiments had closed all the significant loopholes simultaneously. The experiment at Delft University, led by Ronald Hansen, used electron spins separated by 1.3 kilometers, with measurement settings chosen at random and detection efficiency sufficient to rule out the most persistent technical objection. The result? Bell's inequality violated. The experiment in Vienna and a parallel test at the National Institute of Standards and Technology in Boulder confirmed the same result. The local hidden variable picture was not just unlikely, it was dead. In 2022, the Nobel Prize in Physics was awarded to Aspect, Clauser, and Anton Zeilinger for this body of work. The citation was clear. The prize was for demonstrating, conclusively, that the world is not made of definite, locally real properties. The floor is not hidden. The floor is not there. There is a breath needed here, because what this means is not obvious, and what it does not mean is easily misread. It does not mean that nothing is real. It does not mean that everything is connected in some mystical sense. It does not mean that the world is made of mind, or that belief shapes matter, or that distance is an illusion. These are the readings that spread outward from the results like spilled water, filling every available surface. They are wrong. What the experiments showed is more specific and more strange. They showed that no model of the world that preserves both locality, the principle that distant events cannot influence each other instantaneously, and realism, the principle that particles have definite properties before measurement, can reproduce the predictions of quantum mechanics. One of those two principles must be abandoned. The experiments do not say which one. They say only that both cannot be kept. Most physicists have quietly let go of realism. They have let go of the idea that the particle has definite properties before the question is asked. This is the floor being removed, not replaced, removed. And then came Wheeler. John Wheeler, who named the black hole and spent decades living at the edge of what physics could ask, proposed an experiment in 1978 that would make the floor's absence even harder to avoid. He formalized it in 1983. He called it the delayed choice experiment, and the setup is a variant of the standard interferometer. A photon is fired toward a half-silvered mirror that splits it into two possible paths. The two paths travel separately, perhaps for a long distance, and then converge at a second half-silvered mirror at the far end. What happens at that second mirror determines whether the photon's history is recorded as a single path or as an interference of two paths. If the second mirror is in place, the two paths overlap and the photon interferes with itself. The measurement result depends on the relative length of the two paths, constructive or destructive interference, and the photon behaves as though it took both. If the second mirror is removed and detectors are placed at the ends of the two separate paths, the photon registers at one detector or the other, behaving as though it took only one path. This much was already understood. Wheeler's question was, what if the choice of whether to insert or remove that second mirror is made after the photon has already passed the first mirror, after it has, by any classical reasoning, already decided whether to take one path or both? The prediction of quantum mechanics is unequivocal. The photon's behavior at the far end is consistent with whatever measurement choice is made there, regardless of when that choice is made. The photon does not commit to a path in the classical sense at any earlier moment. It remains in superposition until the final question is asked. And the question can be asked after the photon's journey is, classically speaking, already complete. The experiment was realized in 2007 by a team at the Institut d'Optique in Palaiseau, France, working with Alain Aspect, in a setup using single photons in a fiber optic interferometer. The measurement choice was made by a random signal generated after the photon entered the apparatus. The results confirmed Wheeler's prediction exactly. The past is not determined until the question about the past is asked. The photon's history is not fixed. It is, in some genuine and measurable sense, written retrospectively. Wheeler called this the participatory universe. He did not mean that minds create the world. He was careful about this, repeatedly. He meant something more austere and more disturbing, that the act of registering a distinction about the world, any physical act that constitutes an irreversible record, is not separate from the world being distinguished. The apparatus and the photon are not two things, one passively measuring the other. They are participants in one event, and the event cannot be fully assigned to either party alone. There is a phrase Wheeler used late in his life for this idea. It from bit. Every physical thing, every it, derives its existence from answers to binary questions, from bits, from yes or no responses to physical questions posed by the world to itself. He was not being poetic. He was making a precise conjecture about the structure of reality, that the deepest layer is not matter or field or space, but information, the registered distinction, the question answered. The past is not safe. The photon's history is not fixed until the question is asked. And what follows from that, what Wheeler spent his last decades trying to articulate, is what the deepening ahead will trace. And here the architecture begins to reveal itself. Not in physics yet. In physics, what follows is still ahead, but in the structure of the question. If the results of measurements are not properties the particles carry with them, if the past is not settled until the question is asked, if the act of asking is part of the fabric of the event, then what are we dealing with? The stuff of the world, followed all the way to its foundations, turns out not to be stuff. There is a piece of this that rarely enters the popular discussion. In 1961, a physicist named Rolf Landauer, working at IBM's research division in Yorktown Heights, New York, proved something that seems at first like a footnote in thermodynamics. He proved that erasing a single bit of information, truly erasing it, resetting a memory to a known state, requires dissipating a minimum amount of heat into the surrounding environment. Not as a practical limitation of current technology, as a theoretical limit. The act of erasing information has an irreducible physical cost, set by the temperature of the environment and the Boltzmann constant. This result is now called Landauer's principle, and it was confirmed experimentally as recently as 2012 in a laboratory in Lyon using microscopic particles manipulated with laser tweezers. What it implies is easily missed. If erasing information costs heat, then information is not abstract. It is not a bookkeeper's notation laid on top of a physical world, a description one step removed from the reality it describes. It is woven into the physical world at a level where the distinction between physical and informational dissolves. The bit, the yes or the no, the distinction recorded, the question answered, has thermodynamic weight. It shows up in the ledger of entropy. It is as real, in the only sense physics knows how to measure real, as a particle of heat. Information is physical. This sentence sounds obvious until you sit with what it requires. It means that the registered distinction, the measurement, the collapse, the yes or no at the heart of the Born rule, is not a secondary event happening to a primary physical world. It is an event that carries consequences in the physical world's own currency. The asking is part of the fabric. And so we arrive, at the end of this long foundation, at the place where the simulation story is waiting. In 2003, a philosopher at Oxford named Nick Bostrom formulated the simulation argument in its most rigorous form. He showed that one of three things must be true. Either virtually all civilizations at the human level of development go extinct before reaching the computational capacity to run detailed ancestor simulations, or virtually all civilizations that reach that capacity choose not to run such simulations, or we are almost certainly living in such a simulation right now. The argument is careful. It follows from assumptions about computational abundance that are not inherently unreasonable, and it has attracted serious attention from physicists and philosophers who are not inclined toward mysticism, including Elon Musk, who has said the odds are billions to 1 that we are in base reality, and Neil deGrasse Tyson, who has assigned the probability of simulation at above 50%. Take it seriously, sit with it, and then notice what it assumes. Every version of the simulation argument requires a base reality, a substrate, a physical world in which the computer running the simulation actually sits. A world made of definite things, where bits are stored in registers, where currents flow through circuits, where the physical instantiation of the calculation is finally, irreducibly, what it is. It requires, at the foundation, the classical floor, a level of definite, locally real, observer-independent properties that do not themselves require further interpretation. The precisely floor that Bell's theorem and 60 years of experiments have removed. The simulation argument does not fail because it is implausible. It fails because the substrate it requires does not appear to exist. The world, followed to its foundations, is not made of the kind of definite, locally real, classically stable things that could constitute a computing substrate in the required sense. The floor is not hidden, the floor is not there, and without the floor, there is no room for the computer to sit in. This is not a refutation, it is a dissolving. The argument does not get beaten on its own terms. The ground on which it stands turns out not to be there. What replaces the ground is the deepening question. Not whether we are a simulation. That is the small question, the one built for a world with a floor. The large question is what kind of world has no floor, and what it would mean to be real in such a world, and whether there is any word for the thing that remains once the last solid substrate dissolves and does not leave nothing. Those questions are ahead. For now, the foundation is laid. The classical dream is over. The experiments are complete. The result is unambiguous. The electron is still leaning. What follows is the deepening. But the standard story does not close. The experiments are verified. The mathematics works. Bell's theorem stands. The violation is measured, the loopholes are sealed. And yet, the question at the center of all of it, what actually happens during a measurement, what the wave function actually is, what the world is doing between the moments when it is asked about, remains unanswered. Not provisionally, not pending further data, unanswered at the level of principle, in a way that the experiments themselves, so far, cannot adjudicate. This is the honest position. The most precisely confirmed physical theory ever constructed does not have an agreed-upon account of its own meaning. So what does it mean that an electron, not yet measured, holds all paths? What does the wave function represent? Not what it calculates probabilities, and the probabilities are correct. But what it represents, what physical reality it points at, if any. This is the question. It has been open since 1926. It is still open. The difficulty begins with something called decoherence. By the 1980s and 1990s, a partial answer to the measurement problem had been developed, one that satisfied many working physicists, not because it solved the problem, but because it explained why the problem does not seem obvious in everyday life. Decoherence theory, developed in rigorous form by the German physicist Heinz-Dieter Zeh, beginning in the early 1970s and extended by Wojciech Zurek at Los Alamos through the 1980s and 1990s, showed how a quantum system interacting with a large environment loses the interference effects that make it quantum. The mechanism is precise. When a quantum system, say an electron in superposition, interacts with even a small number of surrounding particles, the superposition of the electron becomes entangled with the superposition of those particles. The electron does not collapse. The interference does not disappear in any local sense. What happens is that the phase relationships, the relative angles between the branches of the wave function that allow them to interfere, are scrambled across so many environmental degrees of freedom that they become, in practice, inaccessible. The branches can no longer add up coherently. They can no longer cancel each other out. They decohere. For a macroscopic object, a detector, a cat, a physicist, the number of environmental particles involved is so large that decoherence occurs in timescales far shorter than any measurement could detect. Something like 10 to the minus 20 seconds for a grain of dust in air. The classical appearance of the world, definite, non-interfering, one thing at a time, is not a fundamental feature. It is a consequence of the speed at which quantum interference washes out at large scales. You have stepped out of a building on a winter morning and watched your breath disappear into the air. The individual molecules do not vanish. They disperse. They become part of the environment, inaccessible as a coherent structure, but still present in the entanglement of everything with everything. Decoherence is like that. The superposition does not disappear. It disperses into the environment, too entangled to retrieve, too scrambled to produce visible interference. This is a genuine result. It is not a small thing. It explains why the quantum world and the everyday world feel so different. It explains why Schrödinger's cat, in any real experiment, is not actually in a macroscopic superposition for any measurable time, but it does not close the measurement problem. Not fully. Decoherence shows why the branches stop interfering. It does not explain why only one branch is experienced. The wave function, after decoherence, still contains all the outcomes. They no longer interfere, but they are still there in the mathematics, each branch as real as the others in the equations. What selects the actual result? What picks this outcome rather than that one? Decoherence does not say. The Born rule, the rule that assigns probabilities to outcomes, is still taken as a postulate, assumed as a primitive of the theory rather than derived from its dynamics. The problem has been clarified and localized. It has not been solved. There is something almost vertiginous about this. Standing in a laboratory, looking at a detector that has registered a definite result, knowing that the mathematics that correctly predicted the probability of that result offers no account of why this result and not another. The result is there. The mathematics is silent on its origin. Every physicist who has thought carefully about this reaches the same place. The equations describe a structure. The structure is precise. What the structure is a structure of is not settled. It is worth pausing here, not because the physics is difficult. It is difficult, but because what it is describing is so close to ordinary experience. Every morning you wake up and find a definite world. This room, this breath, this body. Not a superposition of possible worlds, not a leaning across alternatives. A single, definite, unremarkable fact. Physics says this definiteness is not fundamental. It is derived. It emerged somewhere from something that was not yet definite. And where exactly the emergence happened, and what exactly happened means in this context, is the question that has been open for 100 years. So the interpretations persist, and they are not minor variations. The many worlds interpretation, proposed by Hugh Everett III in his 1957 doctoral thesis at Princeton, says the wave function never collapses. Every time a measurement is made, the world, all of it, splits into as many copies as there are possible outcomes, with each outcome realized in some branch. In some branch, the electron hit the left detector. In another, it hit the right. Both outcomes occur. Both are real. The appearance of collapse is just the experience of being in one branch, unable to observe the others. The universe is inconceivably vast, not in space, but in the number of branches, each one as real as the one in which this sentence is being heard. The many worlds interpretation preserves the Schrödinger equation completely. It takes no liberty with the mathematics. It pays for this by postulating an ontology of staggering scale, a reality in which every quantum event forks the universe into parallel copies, continuously at every point in space and time. The physicist David Deutsch at Oxford and the philosopher David Wallace have argued that this is not a cost, but a discovery, that what was previously considered a problem, the profligate multiplication of realities, is simply what the equations, taken seriously, require. Most physicists remain unconvinced. The objection is not to the metaphysics. It is to the difficulty of deriving the Born rule, the probability rule, from the branching structure without circularity. This remains an open technical problem in the many worlds program. Objective collapse theories take the opposite approach. Rather than accepting the equations and multiplying the worlds, they modify the equations. The GRW model, proposed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986, adds a new physical process to quantum mechanics, a spontaneous localization occurring at random that causes the wave function to collapse to a definite state at a rate that depends on the number of particles involved. For a single particle, the probability of spontaneous collapse in any given second is extraordinarily small. For a macroscopic object containing something like 10 to the 23 particles, the collapse is effectively instantaneous. The model reproduces the quantum behavior of small systems and the apparent definiteness of large ones. The GRW model is testable in principle. Its predictions differ slightly from standard quantum mechanics for systems of intermediate size. No experiment has yet been sensitive enough to detect the difference. It remains a serious proposal, but unconfirmed. And then there's the position that many physicists hold privately, more than would admit it publicly. It is often said that the observer creates reality, that what the measurement problem reveals is that consciousness is fundamental, that the mind is the source of the world's definiteness, that quantum mechanics is, at its core, an idealist theory. This reading has been popular since the early days of the theory, reinforced by the fact that several of its founders, including Niels Bohr, Werner Heisenberg, and later Eugene Wigner, made statements that seemed to point in this direction. Wigner, in the 1960s, argued explicitly that the chain of physical interaction that constitutes a measurement can only be closed by a conscious observer, by the act of awareness. The actual claim is more careful and more disturbing than the popular version. What Wigner proposed, following a careful analysis by John von Neumann in his 1932 Mathematical Foundations of Quantum Mechanics, was that the chain of interactions involved in a measurement, particle to detector, to amplifier, to recording device, to human eye, to nervous system, can be described quantum mechanically at every link. And at every link, the Schrödinger equation says, the result is still in superposition. Something, somewhere, must terminate the chain. Wigner's suggestion was that the termination occurs at the point of conscious experience, because consciousness is the one thing in the chain that cannot itself be described as a quantum system in superposition. What the popular version misses is precise. The question is not whether consciousness is involved in the world. The question is, what terminates the measurement chain? and the evidence since Wigner has shifted the weight of the field away from consciousness as the answer. A Geiger counter in an empty room, its result unobserved, its tape unread, its mechanism unattended, still produces a definite outcome that can be found later. The world registers distinctions before any mind is present to observe them. The scratch on the metal surface, the track in the cloud chamber, the mark on the photographic plate. These collapse-like outcomes occur without a watcher. Whatever collapses the wave function, it is not the act of awareness. It is the act of registration, of irreversible change in a physical system. And registration, it turns out, does not require a mind. Wigner later withdrew his earlier position. The popular version has not caught up. What consciousness does to the quantum mechanical picture, if anything, remains genuinely open. But it does not open in the direction the popular story points. Something else does. In 1996, the Italian physicist Carlo Rovelli, working at the Centre de Physique Théorique in Marseille, published a paper that proposed a position more radical than many worlds and more precise than Copenhagen. He called it relational quantum mechanics. His proposal: there is no observer-independent quantum state. Every system has a quantum state, but only relative to some other system. There is no wave function of the universe. There is no view from nowhere. Quantum mechanics is a theory of the information that physical systems have about each other, and every such information relationship is real. But none is absolute. In Rovelli's picture, the electron does not collapse relative to the universe. It collapses relative to the detector, and the detector's state, relative to an outside observer, may still be in superposition. Different systems can have different, mutually inconsistent facts about the same quantum event, and these inconsistencies are not resolved by a deeper, observer-independent layer. There is no such layer. There is only the web of relations, all of them real, none of them absolute. This is strange. It is strange enough that Rovelli himself has described it as requiring a conceptual shift, as significant as the shift from absolute time to relativistic time. The strangeness is the point. It is the cost of taking seriously what the experiments have been saying for a century, that the classical picture of a world with definite, observer-independent properties was not an approximation. It was wrong. But relational quantum mechanics makes explicit something that had been only implicit in earlier interpretations. There is no view from nowhere, not as a limitation of knowledge, as a structural feature of reality. A different approach to the same conclusion arrived from a different direction. In the early 2000s, three physicists, Christopher Fuchs, Carlton Caves, and Rüdiger Schack, developed a position they eventually called cubism, a name derived from the Bayesian approach to probability on which it rests. Their proposal is the most radically first-person interpretation of quantum mechanics that has been seriously defended. In cubism, the wave function is not a description of the physical world. It is not a description of the electron's properties. It is a tool, a mathematical tool used by a specific agent to encode that agent's expectations about the results of measurements. When the agent makes a measurement, the wave function collapses, not because anything physical happens, but because the agent's expectations are updated, as any rational agent would update them in the light of new evidence. The Born rule in cubism is not a law of physics. It is a consistency condition, a constraint on how a rational agent ought to update their expectations to maintain coherence. This sounds at first like a retreat into subjectivity. It is not. What Fuchs in particular has insisted on is that cubism is not saying the world is a construction of individual minds. It is saying that physics is a theory about what agents can expect from their interactions with the world, and that asking for more than this, asking for a description of the world as it is independently of any interaction, is asking for something that the theory, and perhaps any possible theory, cannot provide. The world is real, but its properties are not settled in the absence of interactions that settle them. The bit, the yes or no, is not a discovery of something that was already there. It is a creation of something that was not yet determinate. Stranger than idealism, more disturbing than determinism, and empirically equivalent, in all known cases, to every other serious interpretation. This was formalized in a sharper way by a theorem published in 2018 by two physicists at ETH Zurich, Daniela Fraukiger and Renato Renner. They showed that if quantum mechanics is universally valid, if it applies to all physical systems, including physicists themselves, with no exception for minds or conscious observers, then it is impossible for all agents who use quantum mechanics to reason consistently about each other. Their thought experiment involves two pairs of physicists, each pair measuring the other, each using the quantum mechanical formalism to predict what the other will find. When carried to its logical conclusion, the predictions contradict each other, not as a matter of interpretation, as a matter of logic, given the assumptions. The result is unsettling. It does not mean quantum mechanics is wrong. It means that quantum mechanics, taken at face value, forbids the existence of a consistent third-person account of all quantum events, the kind of account that a God's-eye view of the universe would require. The view from nowhere is not just absent. The theorem says it may be structurally forbidden. It is unsolved. Not unsolved because no one has thought carefully about it. Unsolved at the foundation. There is one more thread. John Wheeler, near the end of his life, returned to the question he had been asking since the 1950s. He asked it in its most compressed form. Why the quantum? Why does the world have this structure and not another? Why are there superpositions at all? Why is there a born rule? These are not questions most physicists ask, because they are not questions that experiments can directly answer. They are questions about the structure of the theory rather than its predictions. Wheeler's conjecture, it from bit, formalized in a 1989 essay, was that the quantum structure of the world is not a brute fact, but a consequence of something more fundamental. That information, in the sense of binary questions answered by physical systems about each other, is the floor, not the atoms, not the fields, not the geometry of space, the asking and the answering. He drew the picture of the universe as a self-excited circuit, a loop with no beginning, in which acts of observation build the structure that makes observation possible. The universe, in this picture, is not a machine that was set running. It is a question that is asking itself. This is a conjecture, not a theorem. Wheeler was clear about this. He did not claim to have proven it, and he did not claim that it resolved the measurement problem. He said it was the direction he believed physics needed to face. And in the years since his death in 2008, the direction he pointed has attracted a body of serious technical work. Lucian Hardy, at the Perimeter Institute in Waterloo, showed in 2001 that all of quantum mechanics can be derived from 5 simple axioms about the information available to observers, about physical systems, plus one postulate that, when modified, gives classical mechanics. The difference between quantum and classical mechanics turns out to be, in Hardy's reconstruction, a single axiom about the relationship between the number of distinguishable states a system has and the number of parameters needed to specify it fully. One axiom. The entire structure of quantum mechanics follows. A decade later, Giulio Ciribella, Giacomo Mauro Dariano, and Paolo Perinodi completed a more comprehensive reconstruction, deriving the full framework of quantum theory from a small set of information theoretic postulates about what physical systems can do with information, how they can be combined, how information can be compressed, how transformations can be reversed. The substrate, they assumed, was not particles, not fields, not space-time geometry. What they assumed was the structure of information exchange. And from that structure, quantum mechanics emerged. The substrate keeps refusing to be matter. And here, physics reaches a point that is rarely named clearly in popular accounts. If information is fundamental, if the structure of what can be known and asked and answered is the floor, then what about time? Time is the dimension in which asking happens. Questions are posed in time. Measurements occur at moments. The wave function evolves in time according to the Schrödinger equation. But there is an equation that sits beneath the Schrödinger equation. When physics attempts to describe the entire universe as a quantum system, when it asks what the wave function of the universe looks like, as required by any complete quantum theory of gravity, it must use the Wheeler-DeWitt equation, formulated by Bryce DeWitt in 1967, and named in part for John Wheeler, who had pushed for it. The Wheeler-DeWitt equation is the most fundamental equation in quantum cosmology. It governs the wave function of the universe itself. It contains no time, not as a simplification, not as a coordinate choice. As a structural consequence of quantizing general relativity, the variable that would represent time cancels out of the equation entirely. The universe's wave function does not evolve in time because, at the level at which the universe is described by this equation, there is no external time for it to evolve in. Time, as experienced from the inside, the before and after, the sequence in which questions are asked and answered, appears to be an emergent feature arising from the correlations between subsystems of the universe that each carry their own internal clocks. Time is not fundamental. Or, more carefully, there is a strong technical suggestion from the most ambitious attempt to quantize gravity that time as physics uses it, as the parameter in which the wave function evolves, is not a feature of the deepest level of description. This is unsolved. Not unsolved because no one has looked carefully. Unsolved at the foundation. The measurement problem requires time, a before measurement and an after measurement, and the deepest equation of quantum gravity has no time in it. These two facts sit side by side without resolution, and will likely continue to do so until a complete theory of quantum gravity exists. No such theory exists. The mathematics is consistent. The derivations are exact. The question, what is the world doing when it is not being asked about, whether there is a world when it is not being asked about, whether that question even has meaning, remains open, genuinely open. Not open as a euphemism for difficult, open as a precise description of where the edge of knowledge is. You have woken at 3 a.m. and lain in the dark, with the room perfectly still, and felt the strange question of whether the room is there in the same way when no one is looking at it. That question is not naive. It is the question physics has been asking in the most careful language available for a century, and the careful language has not closed it. It has made it sharper, more precise, and more strange. The edge is not a wall. It is an opening. What stands on the other side of it is not physics, or not physics alone, but getting to what stands there requires first acknowledging that this is where the edge is, not further in than this. Here, the mathematics is complete. The verification is done. The question of what the mathematics is about remains, with unusual precision, unanswered. And it has been asked before. Not in this language, not in these laboratories, not by these methods, but the shape of the question, what is the world when it is not being looked at? Whether there is a fact about an unseen thing, whether the definite and the indefinite are properties of nature or events in a relation, whether the structure that registers distinctions is in some sense the floor of what is. That shape is older than physics, and it has been approached from the other direction, with tools that are entirely different and entirely its own. Those tools are not mathematics, they are silence, and long practice, and a kind of looking that turns inward rather than outward, that examines the structure of experience rather than the structure of the apparatus, that finds the same absence at the center of the self that physics has found at the center of the particle. Not the same discovery, not the same method, not the same claim, but the same shape of the open question, and the same refusal in the hands of the best practitioners of both to fill the opening with a comfortable answer. The night still has a long way to go, so here is the discipline that must be stated once, at the beginning, before any tradition is named. Physics arrived at a world with no classical floor, no layer of definite, locally real, observer-independent properties at the foundation. Through experiment, through the violation of Bell's inequalities, through the precision of controlled measurement, the contemplative traditions arrived at a structurally similar picture through a completely different method, long, disciplined, systematic investigation of the structure of experience itself, not through experiment in the laboratory sense, through a different kind of rigor, the rigor of the practitioner who sits for years and looks with the same unwavering attention that the physicist brings to the detector, but turned inward rather than outward. These are not the same investigation. The languages are irreconcilable. The methods are incommensurable. The claims the traditions make are not the claims the experiments verify. Physics does not confirm the traditions. The traditions did not predict the physics. What they share is architecture, a pattern in the shape of what each field found when it followed the question of the fundamental floor all the way to where the floor gives way. That is all. And that is not a small thing. The traditions will not be presented as validation of physics. That framing is comfortable and false. They will be presented as parallel investigations that arrived by entirely different routes, at a recognition that is structurally similar to the recognition physics has been working toward for 100 years. The precision of the recognition is what makes it worth attending to. The vagueness of the popular version is what makes the popular version useless. There are 4 traditions. Each one will be allowed to speak in its own terms, at its own depth, with its own hidden content intact. The first is the tradition that has thought most rigorously about what the world is made of when it is not being looked at, and found at the end of that inquiry, not a substrate, but an absence of substrate that is itself the most important discovery the inquiry could make. Sometime in the 4th century of the Common Era, 2 brothers, half-brothers, raised in the same monastery in what is now northwestern India, arrived independently at what would become the most technically demanding school of Buddhist philosophy since Nagarjuna. Their names were Asanga and Vasubandhu. The school they founded is called Yogacara, sometimes translated as the practice of yoga and sometimes as the way of application, though neither translation fully captures what the school claimed. Its central proposition is often summarized as mind only. In Sanskrit, the term is cognition only, vijnaptimatra, meaning that what we take to be a world of external objects is, in the analysis of the Yogacara school, not encountered directly but known only through the structure of experience, through the representations arising in consciousness. This is the moment where most popular accounts of Yogacara stop. And by stopping here, they produce a picture that is almost exactly backwards. The popular version says, Yogacara teaches that the world is in your mind, that consciousness creates reality, that if you change your thoughts, you change what is real, that the mind is the source of the universe. This reading has spread widely in New Age spirituality, in manifestation culture, in the more grandiose versions of you create your reality. It is a misreading so thorough that it inverts what the tradition actually transmits. Here is what Vasubandhu actually taught in his foundational text, the Trimsika, the 30 verses on cognition only, composed around the 4th century. The Alaya Vijnana, the substrate consciousness, sometimes loosely translated as the storehouse consciousness, is not the personal mind. It is not the ego that wakes up in the morning and decides what to think. It is something far more radical, an impersonal stream of conditioned processes that underlies all 8 types of consciousness the Yogacara system distinguishes, and that carries the seeds, the latent impressions from which experience arises. It is the substrate not of a world of objects, but of the pattern of registration and recognition from which the appearance of objects and subjects emerges. And the point of the entire teaching, the operative purpose, the thing the tradition actually transmits as practice, is not to empower the personal consciousness to create a better reality. It is to dissolve the self that believes itself to be the author of experience. The alaya is impersonal. The practice exposes this. What is discovered in the practice is not a powerful creative mind, but the absence of the self that would do the creating. The mind-only teaching is a scalpel, not a throne. It is designed to cut away the illusion that there is a stable subject standing behind experience and producing it. What remains when the cutting is complete is not nothing, and it is not a self with new powers. It is the substrate consciousness recognized as impersonal, as not belonging to anyone, as the conditioned arising of distinctions in the absence of any permanent distinguisher. This is the hidden content. It is the teaching that the lineage holders transmit and that the popular accounts convert into its opposite. The structural parallel to the physics covered so far is not consciousness creates reality. It is something more austere. In cubism, the wave function is not a description of the world. It is a tool an agent uses to encode expectations about what will be registered in interactions with the world. In Rovelli's relational mechanics, properties exist only relative to the systems that register them. The registered distinction, the bit, the yes or no, is what is fundamental, not the object that is supposedly there before the registration. The Yogacara parallel is not identical to either of these. The methods differ. The claims differ. The tradition does not make predictions that can be tested in a laboratory, but the architecture is the same. What appears to be a world of self-standing objects, knowable independently of any registration or relation, dissolves under analysis into something more fundamental. And the more fundamental thing is not a deeper object, but a structure of distinction, relation, and registration that has no stable floor beneath it. The languages are different. The structure is the same. And there is a concrete image the tradition uses, which has persisted across 17 centuries, because it carries something that argument alone does not. Vasubandhu's student Dharmapala described it this way: "It is like the surface of a flowing river on which patterns arise and dissolve continuously. The patterns are real. The arising is real. The dissolving is real. What is not found when you search carefully is any fixed substance underlying the flow, any permanent river stuff on which the patterns are drawn. There is only the patterning. The floor of the river is the river. The second tradition arrived at the same absence by a different route, in a different century, in the same general region of the world. Nagarjuna is the 2nd century Indian monk who broke Buddhist philosophy open for the second time, 200 years after the tradition's founding. He is historically difficult to place precisely, but his central works, and most importantly, the root verses on the middle way, the Mula Madhyamaka Karika, composed in the 2nd century, are among the most technically rigorous texts in the history of philosophy, East or West. His school is called Madhyamaka, the middle way, though the name middle is misleading if it suggests a moderate position between extremes. What Nagarjuna's analysis achieves is something far more radical than moderation. He took every possible position about the nature of things and demolished all four. That things exist, that they do not exist, that they both exist and do not exist, that they neither exist nor do not exist. Each of these positions, Nagarjuna showed, is internally contradictory when applied to the nature of any phenomenon, including consciousness, including the self, including the analysis itself. What remained was not a fifth position. It was the recognition that all four extremes of assertion fail, because they all assume something that cannot be found, a thing with intrinsic, independent, self-standing nature. The Sanskrit term is emptiness, sunyata, but emptiness in English connotes absence, void, a kind of nothingness, and that is precisely what Nagarjuna argued it is not. He was at pains to say that emptiness is not the view that things do not exist. That would be nihilism, the third extreme he demolished. Emptiness is the absence of intrinsic nature. Things arise. They are not nothing, but their arising is always dependent on other things, on conditions, on relations, on the act of designation. And when you search for the thing itself, beneath the web of relations and conditions and designations, it is not found. The search comes back empty. And that emptiness, the absence of the independent thing, is what Sunyata names. This is the teaching that Nagarjuna refused to flatten into a metaphysical position. He refused to say that emptiness exists, because that would make it a thing. He refused to say it does not exist, because that would be wrong. He refused to say it both does and does not, or neither. All four gates are closed. What the analysis produces is not a new doctrine, but the collapse of the conceptual machinery that generates doctrine. The structural parallel to Rovelli's relational quantum mechanics is precise and deliberately limited. In relational QM, there are no observer-independent properties. Every property is relational, real relative to some system, not real in isolation. No property is intrinsic. Everything that exists in dependence on what it is not. The parallel. No thing has intrinsic, self-standing nature. Everything that appears is relational, dependent, conditioned. The Madhyamaka analysis and relational QM are not the same claim. One is a philosophical analysis of the structure of conceptual experience. The other is a physical interpretation of a mathematical formalism. The methods are entirely different, but the architectural finding is the same. Intrinsic, self-standing nature is not what the analysis finds at the bottom. The convergence is architectural. not causal, not predictive. The tradition did not anticipate the physics. The physics does not vindicate the tradition. What both found, at the end of their respective analyses, is an absence of the floor they were looking for, and the discovery that this absence is not a deficiency, but the most important structural feature of the territory. Nagarjuna himself offered no positive description of what emptiness is. He held to the same intellectual discipline that the physicists at the frontier of quantum foundations hold. If the honest answer is that the solid floor is not there, then the honest answer does not then fill the space with a new, subtler floor. It holds the absence. But there is a technical move in Nagarjuna's analysis that most popular accounts omit entirely, and it is the most important one. He did not simply dissolve things into relations and leave it there. He also dissolved relations. He dissolved emptiness itself. In the 24th chapter of the root verses, Nagarjuna anticipates the objection that emptiness is just another metaphysical foundation, that he has replaced things exist with emptiness exists, and left the floor intact under a different name. His response is to show that emptiness is itself empty, that sunyata has no intrinsic nature, that it arises dependently, that to cling to emptiness as a view is to fall into exactly the trap the analysis was designed to expose. He calls this the emptiness of emptiness. This is the level at which the teaching becomes genuinely demanding. It is not enough to understand that things lack intrinsic nature. The understanding itself lacks intrinsic nature. The analysis lacks intrinsic nature. The practitioner who thinks they have gotten emptiness has not yet arrived at what Nagarjuna was pointing at. What is pointed at cannot be held as a position. The tradition uses two levels of truth to hold this: the conventional truth, on which things function and distinctions are drawn and language operates, and the ultimate truth, on which intrinsic nature is nowhere found. Neither truth is more real than the other. The conventional and the ultimate arise together, in dependence on each other, which means the two truths are themselves empty of independent nature. The analysis bottoms out in a recognition that cannot be stated without paradox. Nagarjuna's image for this, from the 27th chapter, is a chariot. If you look for the chariot, you find wheels, axles, frame, spokes. If you look for the chariot in the wheels, you do not find it there. In the axle, you do not find it. In the combination, you find the combination, but no chariot thing above and beyond the parts. The chariot is real. The chariot is used. The chariot carries things. But the chariot, searched for as a self-standing entity with its own intrinsic nature, is not found. What is found is the pattern of parts in relation, and the parts, examined in turn, yield the same result. The floor of the chariot is the chariot. The third tradition is the one that the Orthodox version has tried hardest to contain, and for good reason, because what it says, taken seriously, removes one of the most fundamental assumptions of the religious framework in which it arose. Ibn Arabi was a 13th century Andalusian mystic, born in Murcia in 1165, died in Damascus in 1240, whose total written output runs to hundreds of volumes, and whose central doctrinal proposal, the mainstream of Islamic theology, has alternated between suppressing and sanitizing for 6 centuries. The proposal is called the unity of being, in Arabic, Wahdat al-Wujud, and what it claims is not what the popular version says it claims. The popular version says, Ibn Arabi taught that everything is God, that the world and the divine are one, that there is no difference between the creator and the created. This reading has spread into a kind of mystical monism that sounds, in its popularized form, like an Islamic version of all is one. It is not what Ibn Arabi taught. What Ibn Arabi taught, and what the Orthodox tradition tried to suppress, is something more technically precise and more ontologically disturbing. The core of his teaching is the doctrine of the imaginal realm, in Arabic Hadrat al-Khayal, literally the presence of imagination, but meaning something that is not imagination in the modern psychological sense, an ontological level that is real, that is intermediate between pure non-existence and full material existence, and that is neither the one nor the other. He called this realm the barrier, the barzakh, a term from the Quran that means the partition between two things, neither fully one nor fully the other, holding both sides apart while sharing in both. For Ibn Arabi, the entire world, the manifest universe, exists in this intermediate mode. It is not pure existence. Pure existence is the divine essence, which is beyond all determination and beyond all description, even the description God. And it is not pure non-existence, which would be nothing at all. It is the middle, the realm of qualified existence, of things that are real but not independently real, of forms that manifest from the formless, without the formless ever becoming merely formal. What the Orthodox tradition found dangerous in this is what the analysis implies about the self. If the manifest world exists only in this intermediate mode, as the barzakh, as qualified and dependent reality, then the self that feels most definitely real, most solidly present, most clearly here, is also a form that exists in this mode, not nothing, not unconditionally real, something in between, something that is real as a pattern, but not real as a floor. The Orthodox tradition saw, correctly, that this teaching undermined the firm distinction between the human creature and the divine creator. The doctrine does not say they are the same. It says their relationship is the relationship of a wave to water. The wave is real. The motion is real. The pattern is real. But the wave has no substance independent of the water, and searching for wave substance beneath the pattern comes back empty. The structural parallel to superposition is not obvious and must be drawn carefully. In quantum mechanics, the state between measurements is not nothing and not definite. It is a superposition, a leaning across possibilities, an intermediate that is neither collapsed to one outcome nor simply absent. Ibn Arabi's barzakh names a metaphysical position, an intermediate mode of being that is neither full existence nor non-existence, and in which the manifest world, including every apparently solid thing, permanently resides. The parallel is architectural. One is a physical description of a particle between measurements. The other is a metaphysical description of the mode of existence of everything. The languages are different, the methods differ, but the shape, a real intermediate that cannot be reduced to either pole of the binary, is the same shape. And here is what the 6 centuries of suppression were really about. If the world always exists in the intermediate mode, if definiteness is never the final word, then the religious certainty that requires a world of stable, definite, independently real creatures standing before a stable, definite, independently real God becomes exactly as philosophically untenable as the certainty that requires a world of definite, locally real, observer-independent particles. The intermediate does not resolve into the definite. It is the structure, what the lineage holders of Ibn Arabi's tradition actually transmit. In the commentaries of Sadr al-Din al-Qunawi, his closest student, and in the practice-oriented readings that followed, is a specific form of contemplative attention directed at the barzakh itself. not as a doctrine to be understood, but as a state to be entered, the state of holding two seemingly opposite conditions simultaneously without resolving them into one. The novice is inclined to choose, to decide that something is real or not real, existent or non-existent, divine or human. The mature practitioner learns, through long sitting with this problem, to inhabit the intermediate without resolving it. The Barzakh is not a theological footnote. It is a practice instruction. The practitioner is being trained to tolerate, and eventually to rest in, the ontological intermediate that the untrained mind insists on collapsing. The structural parallel to superposition is not merely architectural at the level of doctrine, it reaches into the operative content. A quantum system in superposition is not really in one state, and apparently in two. It is genuinely in the intermediate, and forcing a resolution collapses it. Ibn Arabi's practitioner, trained in the Barzakh, is being prepared to meet the world without forcing the collapse. The languages are different. The methods differ entirely. But both practices, if practice can be applied to the physicist's restraint in front of the superposed electron, involve the discipline of holding the intermediate without resolution. And there's a fifth thread, briefer than the others, but structurally irreplaceable. In the 7th century, the Chinese monk Fazang, founder of the Huayan school of Buddhism, gave a demonstration to the Empress Wu Zetian that was later recorded as one of the most philosophically efficient gestures in the history of ideas. He built a small room-lined floor-to-ceiling with mirrors and placed a single lamp in the center. Every mirror reflected every other mirror. Every reflection contained the reflections of all the reflections. The lamp's image appeared in every mirror, and in every reflection of every mirror, infinitely deep. Fazang said to the Empress, "This is the structure of reality as the Huayan school understands it. Each part contains the whole. The whole is in each part. Nothing is left outside. But the popular version of Indra's net, the Huayan image of a jeweled net in which each jewel reflects all others, is often presented as a metaphor for the vague feeling that everything is connected. This is the flattening that Fazang would not have recognized. The claim is not vague. It is precise. Each jewel in the net contains not just the image of the other jewels, but the images of their images, recursively, without bottom. The structure is not one of simple connection, but of mutual containment. Each part encoding the structure of the whole in the way that the holographic principle proposes, the surface of a region encodes its volume. The structural parallel to the holographic principle is the closest in the script to being direct. The holographic principle, that the information content of a three-dimensional volume is bounded by its two-dimensional surface, that the interior may be fully encoded in the boundary, proposes something that is architecturally identical to Fazang's Hall of Mirrors. Each lower dimensional slice contains the full information of the higher dimensional interior. The whole is in the part. The interior is in the boundary. The physics is precise. The Huayan claim is precise. The languages are different. The structure is the same. The fourth tradition approached the same opening from the direction of language itself, and found, in the failure of language to reach the floor, the clearest indication of where the floor is not. The Tao Te Ching, 81 short chapters attributed to Laozi, a figure probably of the 6th or 5th century before the Common Era, opens with a sentence that most popular accounts translate smoothly and thereby destroy. The first two lines, "The way that can be spoken is not the enduring way. The name that can be named is not the enduring name." What Laozi is pointing at is not a mystical beyond, a divine realm hovering above the world. He is pointing at the structural limit of language, the limit at which the act of naming stops tracking and starts constructing, and making a claim about what that limit reveals. But the text has been read in two radically different ways, and the difference between them produces what are almost two different philosophies. Most popular accounts of Taoism select one and present it as the whole. The 3rd century commentator Wang Bi read the Tao as pure non-being, the Chinese Wu, the absence of determination, the ground that precedes all distinctions. On Wang Bi's reading, the Tao is the metaphysical source, not nothing, but the undetermined depth from which all things arise, prior to the first distinction, prior to heaven and earth, prior to the categories that make thought possible. The sage who aligns with the Tao aligns with what is prior to the world's self-articulation into the 10,000 named things. The Hashanggong commentary, older, probably Han Dynasty, concerned with the body and breath and the practice of longevity, reads the Tao in an entirely different register. Here, the Tao is not metaphysical background, but an active, immanent process, the rhythm of how things move when they move without forcing. It is as physical as breath. It is what the body knows before the mind adds its commentary. The practitioner of Hashanggong's Tao does not contemplate the void. They attend to the grain of what is happening, the way a skilled craftsman attends to the grain of wood, and move in alignment with a pattern that is discovered in the body of careful practice rather than in the reasoning mind. What most popular accounts of Taoism miss is that these two readings cannot be harmonized. They pull in different directions. Wang Bi's Tao is impersonal, structurally prior, beyond practice in the sense that it cannot be cultivated, only recognized. Hashanggong's Tao is intimate, bodily, available in the felt texture of how things unfold when not forced. One points away from the world toward what precedes it. One points into the world toward what moves through it. The text supports both. The tension between them is not a textual deficiency. It is the most philosophically productive feature of the text, the place where the Tao actually does what it says the Tao does, resists being pinned down, stays undetermined, refuses the single interpretation. The structural parallel to it from Bit and Wheeler's participatory universe is clearest in Wang Bi's reading. If the deepest layer is the undetermined, the Wu, the not yet named, and if naming constitutes a first distinction, a first bit, a first yes or no drawn from the undetermined into the determined, then the Taoist claim and Wheeler's claim share this, that the act of drawing the distinction is ontologically generative. The undetermined is the condition. The named thing is the event that arises when a distinction is drawn upon it. The floor is not a thing. It is the not yet determined from which things emerge when questioned. The parallel is architectural, not predictive. Laozi did not know about wave functions. Wheeler did not derive it from Bit from the Tao Te Ching. Both arrived at the same structural recognition from different directions. The act of distinction is not a description of a world that is already fully settled, but a participation in the settling. The moment when the indeterminate becomes determinate in response to the question. The image the Tao Te Ching uses, in the 11th chapter in Laozi's characteristic compressed style, is the hub of a wheel. 30 spokes converge on the hub, but it is the hollow center that makes the wheel function. Clay is shaped into a vessel, but it is the empty interior that makes the vessel hold. The room is built from walls, but it is the empty space inside the walls that makes the room habitable. What is present is what the hand can touch and measure. What is absent is what makes the present thing useful. The floor of the world in this image is the not there. The absence of the independent substrate is not a lack. It is the precise condition of possibility. So what does all of this mean? Not that 4 traditions from 4 different centuries and 4 different cultures looked at the same quantum mechanical experiments and arrived at the same conclusions. They did not. Not that ancient wisdom anticipated modern physics. It did not. The traditions and the physics arrived at the same shape from the inside out and the outside in. One beginning with what instruments can measure, one beginning with what stillness can reveal, and what they found at the edge of each investigation is the same absence of the solid, self-standing floor. The pattern is specific. It is not vague mysticism. It is not everything is one. It is something more precise and more demanding than that. It is the finding, repeated across methods and centuries, that when you follow the question of the fundamental floor all the way to where the analysis is most careful, the floor is not there, not hidden, not replaced by a subtler floor, not there, and that the thing that is found in the absence of the floor is not emptiness in the sense of nothing. It is the open structure of relation, of conditioning, of dependence, the pattern that emerges when the search for the independent thing has fully failed. The languages are different. The methods differ. The maps were drawn on different continents, in different centuries, by people who had never heard of each other, and the maps look strangely alike. This is not validation. It is recognition, and the honest position is to hold that recognition with the same precision the traditions themselves demand. Not more than what it is, not less than what it is. A structural convergence, a shape repeated at the intersection of the most careful human investigations of the fundamental. Neither field reduces to the other. Neither field validates the other. Both find the same open ground where the floor was expected to be. And that open ground, in the middle of this night, is not an obstacle. It is where the listening is. So here's the honest position. Not a conclusion, a standing place. What the night has traced is not a proof of anything. It is a map. Several maps, actually, drawn by people who never met, in languages that cannot be translated into each other, on questions that their respective methods can approach, but not finally answer. The maps converge. The convergence is real. And it is not enough on its own to resolve anything, which is itself one of the most important things it is possible to say after 100 years of quantum mechanics and 2,000 years of contemplative inquiry. So, what does the convergence mean? What can be said plainly? What can be said only tentatively? What cannot be said at all? These are different questions. They deserve different answers. And the discipline of keeping them separate, of not letting the weight of the convergence smuggle in more certainty than the evidence licenses, is the most important discipline this night has tried to model. What is established is this, not what is claimed, not what is suggested, what is verified in controlled experiments with results that have been replicated across 60 years and confirmed beyond any reasonable scientific doubt. Bell's theorem has been tested. The loopholes have been closed. The experimental record from Clauser and Friedman in 1972, through Alan Aspect in 1982, through Ronald Hansen in Delft in 2015, confirmed by the Nobel Prize in 2022, is unambiguous. Local hidden variable theories are wrong. The world does not contain, at the foundational level, a layer of definite, locally real properties that particles carry with them independently of measurement. This is not an interpretation, it is a result. The floor of locally definite properties is gone. This cannot be undone by a new interpretation of quantum mechanics. Every serious interpretation must accommodate this fact, because the experiments that establish it are not interpretation dependent. Superposition is real. Interference is real and measured. Entanglement is real and measured. These are not metaphors for quantum strangeness. They are the precise, quantified behavior of particles that has been confirmed in thousands of experiments across 60 years, at scales ranging from individual photons to macroscopic superconducting circuits. The world at its finest scale does not behave classically. The classical picture is an approximation, valid at the scales where decoherence makes quantum behavior effectively invisible, and false at the scales where it has not yet occurred. Decoherence is real. The mechanism by which quantum systems lose their interference properties through entanglement with their environments has been confirmed in controlled experiments. It explains why the quantum world and the everyday world have different textures. It does not explain why only one measurement outcome is experienced. That boundary between the decoherence that removes interference and the selection of the single result is exactly where the measurement problem lives. Information has thermodynamic weight. Landauer's principle is confirmed. The bit, the registered distinction, has irreducible physical consequences. This is established. What is suggested, not proven, not established, but seriously pointed toward by the evidence and the theoretical structure, is something harder to say without overclaiming. The evidence suggests that information may be more fundamental than matter, not information in the colloquial sense, not data, not language, not knowledge in a human mind. Information in the technical sense, the structure of what distinctions a physical system can register in its interactions with other physical systems. The framework in which physics is conducted may need to be rebuilt not from particles or fields, but from what those particles and fields do. Register distinctions, answer questions posed by their interactions, establish correlations that accumulate into the appearance of a stable world. The reconstruction theorems of Lucian Hardy and of Ciribella, D'Ariano, and Perinotti point in this direction. They showed that the entire mathematical structure of quantum mechanics can be derived from information theoretic postulates, axioms about what agents can and cannot do with physical information, without assuming particles, without assuming space-time, without assuming any of the usual physical furniture. The theory emerges from the structure of the asking and answering. This is a suggestion, not a proof. The derivation shows that if you assume this information theoretic structure, you get quantum mechanics. It does not prove that the information theoretic structure is the floor. The direction of implication is not reversible. But the suggestion is serious, and it is made by serious people working with precise mathematics. The holographic principle suggests something equally strange at the other end of the scale. Gerard 't Hooft at Utrecht and Leonard Susskind at Stanford showed in the early 1990s that the information content of a three-dimensional region of space is bounded not by its volume, but by its surface area, not approximately. As a matter of principle, you cannot pack more information into a region than its boundary can hold. Juan Maldacena, in 1997, made this precise in a specific mathematical context, the ADS-CFT correspondence, showing that a quantum gravity theory in a three-dimensional space is exactly equivalent to a quantum field theory living on the two-dimensional boundary of that space. The interior is dual to the boundary. The depth is not primary. What looks like three-dimensional reality from the inside may be two-dimensional information from the outside, if there were an outside. There is no outside. The holographic principle is not saying the world is a two-dimensional projection on a screen somewhere. It is saying something more unsettling, that the concept of interior and depth may not be fundamental, may be derived from a more basic structure that does not have depth built into it. This is suggested. It is not established. It remains one of the most serious open conjectures in fundamental physics. Relational quantum mechanics and cubism suggest, each in its own precise technical language, that there may be no observer-independent quantum state, no view from nowhere, no third-person account of the universe that is available to a perspective that does not participate in what it describes. The Froschiger-Renner theorem makes this structural. If quantum mechanics is universally valid, a consistent third-person account of all quantum events may be forbidden, not just unavailable. This is suggested. It is not established. There is no experiment that has directly confirmed it. But these positions are consistent with everything that has been experimentally tested, and they take the experimental results more seriously than interpretations that patch the equations with additional structure the experiments do not require. And there is something worth sitting with in this suggestion before moving further. The no view from nowhere is not simply an epistemic limit, not just a practical difficulty of getting outside the universe to look at it from the outside. It is a structural consequence, if relational QM and cubism are correct, of the very nature of what properties and facts are. Properties are relational. Facts are perspectival. There is no vantage point that is not also a participating system. This is not mysticism. It is a careful technical proposal made by serious physicists, derived from the experimental record. And it is a proposal that finds, when you look across the traditions this night has traversed, something like a family resemblance. The same structure that Ibn Arabi found when he said the world exists only in the intermediate mode, that Nagarjuna found when he said no, thing has intrinsic independent nature, that Ravelli found when he said properties exist only relative to other systems. Not the same claim, the same architectural shape. What the experiments do not require is a floor. The floor is not required. It is not there. There is a particular quality of vertigo in arriving here. Not the theatrical vertigo of a mystery novel, the breathless, excited vertigo of imminent revelation. A quieter kind. The vertigo of a long walk that has brought you to the edge of a cliff, in fog, in the dark, without drama. The edge is real. The fog is real. The darkness is not frightening. It is just the limit of what the lamp carried this far can illuminate. The vertigo is the honest recognition that the floor you are walking toward is not there, and that what stands in its place, if stands is even the right word for something with no substrate, is the open question itself. Hold this for a moment, not as a conclusion, as a fact. The floor is not there. What this means is still being worked out. And what remains genuinely unknown is the deepest part of what this night has been about. The measurement problem is open. It has been open for 100 years. Not open as a provisional state waiting for the right idea to arrive. Open as a structural feature of the current framework. The Schrödinger equation does not predict when or why a definite outcome occurs. Every time a measurement is made, the equations say the whole system, particle, detector, physicist, remains in superposition. What resolves the superposition into a single outcome is not described by any term in the equation. The Born rule tells you the probability of each possible outcome. It does not tell you why there's only one outcome in any given experiment, rather than all of them. No interpretation of quantum mechanics that has been proposed has been confirmed to be correct. Many worlds, Copenhagen, cubism, relational quantum mechanics, GRW objective collapse, Bohmian mechanics, they are empirically equivalent in every regime that has been tested. The question of which one, if any, is right is not a question physics can currently answer. Anyone who tells you otherwise is selling something. The problem of time is open. The Wheeler-DeWitt equation, which governs the wave function of the universe in any complete quantum theory of gravity, contains no time variable. This is not a notational choice. It is a structural consequence of quantizing general relativity. The constraint that removes time from the equation is the Hamiltonian constraint, which encodes the diffeomorphism invariance of general relativity, the fact that no time coordinate is preferred. The universe's wave function at this level does not evolve. There is no external time for it to evolve in. Time, as experienced as the sequence in which causes precede effects and questions precede answers, appears to be an emergent property of the correlations between the universe's subsystems, each of which carries its own internal clock. But how exactly time emerges from a timeless equation, and whether the emergence is fundamental or approximate, and what it means that the most complete equation of physics has no place for the dimension in which all the measurements occur. This is genuinely unsolved. The measurement problem requires time, a before measurement and an after measurement. And the deepest equation of quantum gravity has no time in it. These two facts sit together without resolution. The nature of the convergence itself is unknown. Whether the structural parallel between quantum foundations and the contemplative traditions reflects the structure of what is, or the structure of how human minds investigate anything, or something that cannot be cleanly separated from both. This is not a question physics or contemplative practice can currently answer. The convergence is real. The inference from the convergence is not settled. And the substrate, what underlies everything, if anything underlies everything, is unknown. There is no confirmed account. There is no experiment that has identified the floor. There is the consistent experimental result that the classical floor does not exist. And beyond that, there is the silence where the floor was expected to be. And in the silence, several proposals, none of them confirmed, all of them serious. What the convergence between physics and the contemplative traditions means, what it actually implies about the nature of reality, is unknown. The convergence is real. The structural parallel is precise. But the inference from these investigations found the same shape to the shape is the shape of something real, requires additional premises that no one has supplied. The convergence could reflect the structure of what is. It could reflect the structure of how human inquiry works. It could reflect the limits of what any investigation can find, regardless of what lies beyond those limits. These three possibilities are not easily distinguished. There is no experiment or contemplative practice that has definitively separated them. And there may not be one, not because the question is too hard, but because the question may be the kind that cannot be settled from inside the instrument that raises it. This is not a defeat. It is a precise and honest description of where the edge of knowledge is, not further in than this. Here, the map ends here, and what lies beyond the edge is not mapped. This is what it looks like when inquiry is done with integrity. Here is the objection that deserves to be named. A careful materialist, confronted with the convergence between quantum foundations and the contemplative traditions, would say, the human mind evolved to find patterns. It finds patterns whether or not the patterns reflect reality. The contemplative practitioner and the physicist are both human beings, working with human nervous systems, producing results that are constrained by the same cognitive architecture. Of course, they find similar shapes. They are looking with the same instrument. The convergence is a fact about the instrument, not about the territory. This objection has force, real force. It cannot be dismissed with a gesture toward the precision of the parallel, because the objection is precisely about whether precision in a human instrument tells us anything about what lies outside the instrument's constraints. The fact that 3 traditions on 3 different continents found the same structural absence at the foundation of things could be remarkable evidence of a genuine absence. It could also be evidence that all human minds, when pushed to their limits of analysis, produce the same failure mode, the same collapse of the conceptual machinery into a recognition that the machinery has run out of resolution. The absence found may be the absence of the concept, not the absence of the thing. And the strict contemplative, from the other direction, would say, the parallel between quantum mechanics and the traditions is not a discovery. It is a flattening. The traditions do not describe the structure of physical reality. They prescribe a practice for the dissolution of the self that suffers under the illusion of solidity. To find a structural parallel between Nagarjuna and Bell's theorem is to treat the Madhyamaka teaching as a set of propositions about physics, which is to miss the entire point, which is not propositional at all. What Nagarjuna points at cannot be found by following the equations. It can only be found by the kind of looking the tradition trains, and that kind of looking is not equivalent to running an experiment. Both objections are correct in what they affirm. The materialist is right that the convergence could be instrumental rather than ontological. The contemplative is right that the traditions are not making claims about the same territory physics investigates. These are real limits on what the night has established, and the honest position is to let both limits stand, not to rescue the listener from them, not to supply a counter-argument that dissolves them. The convergence is what it is, a structural recognition, precise, specific, repeated across centuries and cultures, found at the edge of the most careful human investigations of the fundamental, and genuinely ambiguous in what it implies, whether it tells us something about the nature of things, or something about the nature of us, or something that cannot be separated from both. This remains open, genuinely, irresolvably open, at least for now. The mystery is not a problem to be solved. It is the ground on which the asking happens. There is a kind of relief in that, if you let yourself feel it. Not the relief of an answer, the relief of the question finally stated clearly enough that no further pretense is required. What physics knows, it knows with extraordinary precision. What it does not know, it does not know. What the traditions know, they know in the register of the practitioner's direct recognition, and what they do not know, they do not claim to know. The pretense that either field has fully closed the question is what the careful work of both fields, followed honestly to its edge, refuses. And this night is not the first time this ground has been felt. You have been here before, not in a lecture hall, not in a monastery, but in the ordinary moments when the floor of the ordinary day gave way and something else was briefly visible beneath it. The moment of recognition that arrived without summoning, when the usual sense of being a solid self in a solid world thinned, and what was there underneath was not nothing, but something with no good name. The experience, falling asleep, of the boundary of the self becoming indeterminate, not anxious, not alarmed, simply loosening at the edges, the way a held breath releases, the way a clenched hand opens in the dark. These are not evidence of anything. They prove nothing about the measurement problem. They confirm no interpretation of quantum mechanics. They do not validate the traditions. The honest position requires saying this clearly and then continuing. The fact that they prove nothing does not mean they are nothing. They are the closest most human beings come, in the course of an ordinary life, to standing where the physicists and the contemplative stood, at the edge of what ordinary language and ordinary assumption can hold, looking at something that is there but cannot quite be named. The physicists found it at the scale of the electron. The contemplatives found it at the scale of the self. What you have felt is neither of those scales and both of them. The ordinary, familiar dissolution of the hardest boundary you know. The boundary between the one who is experiencing and the experiencing itself, loosening in the dark without drama. That loosening is not spiritual progress. It is not evidence of enlightenment. It is not proof of the quantum nature of consciousness. It is simpler than all of those things, and more reliable. It is what happens when the day's insistence on definite things finally releases, and the world is briefly what physics and the traditions have separately been saying it was all along, not made of the solidities we navigated through all day, but of something lighter, more relational, more temporary, resting on no floor that can be found by digging. There is nothing to do with this, nothing to remember, nothing to hold. The traditions that looked at this most carefully said the same thing, that what is found at the ground cannot be carried away as a possession, cannot be installed as a view, cannot be deployed as a technique. What it can do is be the ground on which the ordinary day rests, whether or not the ordinary day knows this. The table does not know what it rests on. The lamp does not know. The breath does not know. And yet they rest there. That is part of the point. The traditions do not ultimately offer a technique for holding the recognition. They offer a way of being with it that does not require holding. The physics does not offer a prediction about what you will experience in the moment before sleep. It offers a description of the structure in which the experience occurs. Both of these are less than the experience, and neither of them is the experience. The experience is its own thing, happening in its own way, requiring no authorization from any field. What remains is the room, the breath, the weight of a body at rest on a surface that rests on no deeper surface than the world offers, and the world offers none. In the silence before sleep, the mind sometimes does something that the waking day does not permit. It releases the investment in the next moment. The future, what will be said, what will be done, what must be remembered, loses its grip briefly, and what is left is the present without its usual frame of before and after. This is not a mystical state. It is the ordinary neurological loosening that precedes sleep. But it is worth noticing what the loosening reveals, however briefly, that the ordinary state of the waking mind is not the neutral baseline it presents itself as. It is a continuous construction, a continuous insistence on the reality of the floor, and the loosening is the floor releasing as it releases every night without drama, without announcement, into the open ground that was there the whole time. This is not evidence of anything. It does not prove the contemplative teaching. It does not confirm the physics. It is simply a thing that happens every night to the one now listening. The daily dissolution of the constructed solidity of the self and the world, and the return, in sleep, to whatever precedes and underlies that construction. The traditions called it different things. Some called it the ground. Some called it the unborn. Some called it the substrate consciousness settling back into its impersonal depth. Physics does not have a name for it, because physics does not study the subjective register of decoherence occurring in a human nervous system. But the shape is familiar from the other direction. The definiteness releases. The spread remains. No one is looking. The question has not yet been asked. The table and the lamp are still there. Or they are not. The room is dark, and darkness does not confirm the things it contains. The breath is slow. The boundary between the one listening and the listening itself is already thinning, the way it does at this hour, in this state, without being asked. The electron is still leaning across its paths. Not here, not there, not yet a fact. The superposition has not collapsed. The question has not yet been asked. What was expected at the center was a floor. What was found was the asking, not the answer. The asking itself. The world drawing a distinction, registering a bit, posing to itself the yes or no that constitutes the next moment of what is. The self that expected to find the floor has loosened. The question is still there. The ground on which the question rests is not a thing, not nothing, not a deeper floor, the open ground itself. There is no floor beneath the world, and the place where the floor should be is not empty, but the open ground on which everything, including the one now listening, is quietly and ceaselessly being drawn.